Okay, it's 8 o'clock. Let's begin. So today we'll be going through reactivity series. Today's crash course is on reactivity series. So our agenda, we're focusing on the reactivity series, the displacement reaction. Okay, then there will be MCQ and structure question for you to try. Then we'll move on to thermal effect on carbonates. Okay, then extraction of metal and prevention of rusting. Okay, so for all these subtopics, right, I have a few analogies for you to grasp the concept. Okay. Then at the end, there'll be a Kahoot quiz to test your knowledge. And for those who come for my crash courses for the first time, there's a feedback form at the end as well. So please fill the feedback form up, and yeah, it helps me to improve as well. Okay. So without further ado, let's begin. Can everybody hear me? If can hear me, please give me a thumbs up. Then I'll begin now. Okay, so reactivity series is basically ranking. It's like a ranking system. You're ranking the most reactive metal versus the least reactive. Okay, so I'm pretty sure your teacher has already given you like a few memory shortcuts or acronyms to remember the whole reactivity series. Remember, it is please stop calling me cool, zebra, highlight, happy, cute, and okay, so you don't have to follow this method of memorizing, but if you already have if you don't have any method yet, you can use this. Okay, so P will be potassium, S will be sodium. Okay, sorry, somebody wants to enter. Okay, so P will be potassium, so S will be sodium, C will be calcium, M will be magnesium, then C is carbon. Okay, so carbon is not a metal. Carbon is not a metal, but it's just used to compare the reactivity. Okay, because later we'll be looking at carbon as one of the comparison. Okay, then zebra will be zinc, I will be iron, L will be lead, H will be hydrogen, C will be copper, and A is silver. Okay, so it's like a ranking system from the best to worst, but this is not best to worst. This is most reactive to least reactive. Okay, so your most reactive is potassium, and your least reactive is silver. Okay, now that we understand what is the reactivity series, let's move on to the displacement reaction. Okay. So how displacement works is the more reactive metal, it has a greater tendency to lose electrons to form positive ions, right? We know that metals lose electrons to form positive ions, okay, or cations. Right, so the more reactive the metal, the greater tendency for it to do that. Okay, the greater the tendency of the atom to lose electrons to form positive ions. Okay, so this can be observed in a displacement reaction where more reactive metal can displace any less reactive metal. Okay, from its salt solution. So for example, you have zinc plus copper 2 sulfate. Okay, if we look at the reactivity series, zinc is above copper, right? You compare these two, zinc and copper. Zinc is above copper. So we can say that zinc is more reactive than copper. Okay, because it is more reactive than copper, it can displace copper from copper 2 sulfate. Okay, so I want you to think of this analogy. Let's say you are at a workplace, right? Okay, then you have person A versus person B. Okay, then right now person A, right, holds a managerial position. Okay, so person A holds a managerial position in the company, right? Then person B is fighting for this position. Okay, person A already has the managerial position, but person B is fighting for this managerial position. And it just so happens that person B is actually more competent than person A. Okay, person B is more competent than person A. So person B can replace person A position as a manager. Okay, so since B is more competent than person A, B can replace A for this position. Okay, then now we think about chemistry, right? So instead of being more competent, it's more reactive. Okay, so because zinc is more reactive than copper, because B is more competent than A, then zinc can displace copper from the salt solution, okay, from copper to sulfate. So this is an analogy you can use to understand displacement. Okay, so what happens after displacement? Because zinc replaced copper, now it will have zinc sulfate. Okay, so now zinc sulfate is your salt solution, and copper will be as an element by itself, as a metal. Okay, so there are two observations for this, right? The first observation is a pink solid is formed. Okay, firstly, observations, right? We are talking about what we can see, hear, and smell. Okay, these are observations. So if the question asks you about observations, make sure you can see it, make sure you can hear or smell. So firstly, we can see that a pink solid forms. So this pink solid is actually copper. Okay, then what's the second observation? You realize we changed from copper 2 sulfate to zinc sulfate, right? Copper 2 sulfate is actually a blue solution, right? Because it contains copper 2 ions. So blue solution turns colorless. That is the second observation. Okay, so for displacement questions, 99% of the time, right, they will test you on observations. So just make sure that the observation is something you can see, hear, or smell. Okay. So it works the same for oxides. A more reactive metal in the reactivity series, it can displace a less reactive metal from the oxide. Okay, so if we use back another example, right, we have iron and copper 2 oxide. So we're going to compare the two metals, iron and copper. Okay. So we have iron and copper. Obviously, iron is more reactive than copper because iron is above copper in the reactivity series. Okay, iron is above copper in the reactivity series, so it's more reactive than copper. So it can displace copper. Okay. So iron is more reactive than copper. So it displaces copper from copper 2 oxide. Okay, you always displace a metal from its oxide or you displace a metal from its salt solution. Right? So this is a simple explanation. So you can link back to the analogy, right? Just like how a more competent person will replace another person who is less competent for a certain higher up position. Okay. So any questions so far? Let me know if I'm going too fast. Do we need to memorize the color of the salts? Yeah, so most of the color of the salts, right, is already from the qualitative analysis. So if you remember the test for cations, right, those solutions, those precipitates, yeah, you have to know the colors. When my school memorized, we have carbon and hydrogen. Yes, we have carbon and hydrogen. So it's over here. You have carbon here and hydrogen here. So you can use this acronym to remember, or if your school gave you an acronym, you can use it to remember as well. Okay, any other questions? Okay, if not, can you guys try question 1 and 2? I'll give you all 6 minutes. Okay. All right. It's 8:16. I'll be going through the questions. Question 1. Pieces of lead, magnesium, iron, and an unknown metal X were placed separately in test tubes. Okay, so we have 4 metals. Okay, we have 4 metals. And placed separately in test tubes containing aqueous solutions of their ions. Okay, so it's definitely testing us on displacement reaction. Okay, because when you place metals into an aqueous solution, you are testing whether the metal will displace the other metal from the aqueous solution or not. Okay, so the following observations were made. A tick means a reaction occurs, and a cross means a reaction does not occur. Okay, so if a reaction occurs, that means what? If reaction occurs means the metal is more reactive than the other metal, okay, in the salt solution. So let's look at the first one. For lead, right? Cross, 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 cross. Lead could not displace any of the other metal ions. Okay, so we can say that lead is the least reactive. Okay, least reactive. So immediately I can cancel out C and D, right? Because lead is the least reactive. Okay, then next we got magnesium, right? Magnesium, it has a reaction with lead ion, right? Lead 2 ion. So it displaces lead 2 ion. Then it has a reaction with iron 2 ion. So it displaces iron 2. And then it also has a reaction with X2 plus ion. Okay, so this shows that magnesium can displace all the 3 other ions. That means it is more reactive than the other 3 ions. Okay, so it is the most reactive. Okay, magnesium is the most reactive. Then iron, right? Iron, it can displace lead. It cannot displace magnesium, cannot displace iron, and it can displace X. Okay, so there's 2 ticks, right? It can displace lead and X, but it cannot displace magnesium. So we can say it is more reactive than lead, it is more reactive than X, but it is less reactive than magnesium. Okay, so it is second most reactive. Okay, why is it second most reactive? Because it is more reactive than 2 other metals. We have only 4 metals, right? And you're comparing 1 to 3 other metals. So if it's more reactive than 2 other metals, it is the second most reactive. And then finally, your last one, X. It can displace lead and it cannot displace the others, right? So it is the third most reactive. Okay, because it is only more reactive than lead, which gives us the answer A. Okay, you have magnesium, which is your most reactive. Then second most reactive is iron, third most reactive is X, and fourth most and least reactive is lead. Okay, so your answer is A. Right. If there are no questions, I'll move on to question 2. Okay, so don't worry if you cannot copy down everything because I'll be sending this this whole answer key by tomorrow. Okay, with all the annotations and inkings. Right. So question 2, the following experiment was set up. So we have copper, we have a metal strip, right? Placed in a aqueous solution. Okay, all these are aqueous solutions. So immediately you have metal and you have aqueous solution. You're probably testing me on displacement reaction. Okay, so it's always important to identify what the question is trying to test you on, right? Once you can identify it, then you know what concepts to apply. Okay, so since we know it's displacement, we have to compare the reactivity of the metals. Okay, then let's see what the question asks us. State the beakers which did not have a visible reaction. It did not have a visible reaction. So if there's no visible reaction, that means there's no displacement. And if there's no displacement, that means the metal has to be less reactive than the other metal in the solution. Okay, the metal that is entering the solution has to be less reactive than the metal in the solution for there to be no visible reaction. So let's compare copper and silver. Okay, if we look at the reactivity series, copper is more reactive than silver. Okay, so there is definitely a reaction, and the observation will be that copper is formed. Okay, because the observation is silver is formed. Okay, because copper displaces silver from the solution. Then next we have silver and calcium. Silver is less reactive than calcium, right? If you look at the reactivity series, silver is below calcium in the reactivity series. So it cannot displace. Since silver is less reactive than calcium, Ag cannot displace calcium. Okay, silver cannot displace calcium. So the beaker that has no visible reaction will be beaker B. Okay, but just for safety reasons, I always check the rest. So we have calcium and magnesium. Again, we look at the reactivity series. Calcium is above magnesium in the reactivity series. So calcium can displace magnesium. So there's going to be a reaction. Okay. So I'm just going to put a tick for those that has reaction. This one has reaction, this one has reaction. And finally, magnesium and copper. Okay, so if you look at the reactivity series again, magnesium is more reactive than copper because it's above copper in the reactivity series. So there is a reaction and copper will be formed. Okay, so your answer is beaker B. Then next, they want you to construct the ionic equation for beaker D. Okay. So for ionic equation, right, there are a few steps. First, you have to write out the chemical equation. Okay. So I'm going to write it out. Okay, I'll write here first. Okay, the first step of writing an ionic equation is always to write the balanced chemical equation first. Okay, so after I write this, I check, is it balanced? So we have magnesium, copper. Yeah, the equation is balanced. Okay, then the next step is to break down the aqueous solutions. Right, we're going to break down the aqueous solutions into ions. And then we leave the rest the same. Okay, so I'm going to put it here. So magnesium is solid, so we're not going to break that down. Copper 2 nitrate, yes, it is aqueous, so we can break that down into ions. Right? Okay, then magnesium nitrate is also aqueous solution. So I can break it down. Sorry, let me make this longer. Okay, then copper, I leave it alone. So now that I've broken down the aqueous solutions, the third step is to remove the spectator ions. So what are spectator ions? Spectator ions are basically those ions that don't take part in the reaction. They only spectate. Okay, so those ions that don't take part in the reaction, they will be on the left side and the right side. Okay, so we have nitrate, 2NO3 on the left side, and 2NO3 minus on the right side. So I'm going to remove it. Those are my spectator ions. Okay, and then there you have your final equation. Right, so this is your ionic equation for beaker D. Mg plus Cu2 plus to give you Mg2 plus Cu. Okay, it's showing the ions that take part in the reaction. Okay. Now, describe and explain your observations in beaker D. Okay, there's two things. One is to describe, one is to explain. So remember I mentioned earlier, what should you focus on for observation? Focus on something you can see, hear, and smell. Okay, see, hear, and smell. Okay, do we have a question? Don't we need state symbols for part B? Okay, if the question does not ask to give state symbols, it is optional lah. Okay, but it is a good habit lah to write state symbols. So magnesium will be solid. Copper 2 plus will be aqueous because it's an ion. Magnesium 2 plus will be aqueous as well. And copper will be solid. Okay, so if the question does not ask you to write state symbols, I highly recommend you don't write lah, because might have mistakes. But if the question asks you to write, then of course you write. Okay. Then describe and explain your observations in beaker D. So remember, observations is something you can see, hear, and smell. Okay. So firstly, what happens, right, when magnesium reacts with copper 2 nitrate? It forms magnesium nitrate and copper. Okay, so copper is your pink solid. So first observation, a pink solid is formed. Okay, a copper is formed. Then second observation will be the color of the solution. Copper 2 nitrate is blue in color, right? This is a blue color solution. And it becomes what? It becomes magnesium nitrate. Magnesium nitrate is a colorless solution. Okay, because magnesium doesn't have any color that we have learned. But for copper, we learned that copper 2 plus will give blue solution. Okay, so as for the described observations, there's two things. One is pink solid form. Second one is blue solution turns colorless. Okay, so I'm stating what I can see in this case. Then to explain, let me paste it inside. To explain the reason, right? We talk about the displacement reaction. Okay. So first, the description is a pink solid is formed and the solution changes from blue to colorless. Okay. The reason is because magnesium is more reactive than copper, right? So magnesium can displace copper from copper 2 nitrate. Okay, it can displace copper from copper 2 nitrate to form copper and magnesium nitrate. Sorry, this one should be. Okay, I'll be moving on now. Okay, now we move on to thermal effect on carbonates. Okay, so there's a reaction for this. It is basically the metal carbonate decomposing lah. That's what it means by thermal effect on carbonates. So the reaction is the metal carbonate, when it decomposes, it will form metal oxide plus carbon dioxide. Okay, so for example, we think of calcium carbonate. If calcium carbonate decompose, it will be calcium carbonate decomposed to form calcium oxide plus carbon dioxide. Okay, so this is a chemical equation that you have to remember. And basically, okay, somebody wants to join. Okay, basically the more reactive metal, right, the greater the resistance to decompose by heating. Okay, in other words, the metal carbonate will be more heat stable. So let me give you an analogy for this. The fridge versus magnet analogy. Okay, so I'm sure every one of you here have a fridge at home, right? A fridge. Okay, this doesn't look like a fridge, but let's say it's a fridge. Then you put magnets on the fridge, right? Okay, so this is your magnet. And then this is the fridge. So think about this. The stronger your magnet, right, there'll be it will be more strongly attracted to the fridge. Okay, so there will be stronger attractive forces for a stronger magnet to the fridge now. And then it will be harder to remove the magnet, correct? Right, the stronger magnet attracted to the fridge, and it's harder to remove the magnet from the fridge. Same thing for the metals, right? The metal carbonate. You think of the magnet as a metal. Okay, think of the magnet as a metal. Then think of the fridge as your carbonate. So let's say your metal, right, is more reactive, then it will be attracted to the carbonate even with greater attraction, right? There will be more strong attractive forces between the metal and the carbonate. So it is harder to separate them. That's why we can say there is greater resistance to decompose. Okay. So the more reactive the metal, the harder it is to decompose by heating, right? The harder it is for the carbonate to decompose by heating. Just like the magnet analogy, right? The stronger the magnet, the harder it is to remove from the fridge. Okay, so in other words, the metal carbonate with the more reactive metal, it is more heat stable. Okay, it's more heat stable. It doesn't decompose easily by heating. Okay, so carbonate compounds containing group 1 metals. Okay, so group 1 metals are all your metals here. Your lithium, sodium, potassium, all these. Okay, carbonate compounds containing group 1 metals are very heat stable generally, right? Because your group 1 metals are very reactive. Okay, they are very reactive, so the carbonate that they form, right, will not decompose so easily. Okay, I hope that you can use this analogy to understand thermal effect on carbonates. So any questions for this concept? Okay, if no questions, I want you guys to try question 3. Okay, I'll give you 5 minutes. Okay, so I have some of you answering the questions in the in-call messages. That is good. Okay, 1 more minute, 8:40, then I go through the questions. All right, 8:40, I'll go through the question now. The diagram below shows an experimental setup to investigate the thermal effect on carbonates. Okay, so we have this test tube here containing carbonate P, and then there is heating involved, and then we have lime water here. Okay, so lime water is actually used to test for carbon dioxide. Okay, the table below, okay, wait, let me draw this nicer. Okay, the table below shows the results of the experiment using different carbonates P. Okay, so we have sodium carbonate, zinc carbonate, calcium carbonate, copper 2 carbonate, and then the observation in lime water. So there's no visible change for sodium carbonate, and for the rest, there is a white precipitate form. Okay, so if there's a white precipitate form, means that carbon dioxide is present. Okay, if carbon dioxide present, that means the carbonate decomposed. Okay, now that we have analyzed the question, let's look at what they ask. Write the chemical equation to show the thermal effect on calcium carbonate. Okay, so calcium carbonate will decompose to form calcium oxide plus carbon dioxide. Okay, let me just adjust the things. Okay, so your calcium carbonate, right? It decomposes to form a metal oxide and carbon dioxide. So your metal oxide is calcium oxide. Okay, which carbonate given in the table is the most heat stable? Okay, remember we talked about heat stable is usually the carbonate with, it is the carbonate with the more reactive metal, right? Because the more reactive metal has the stronger forces with the carbonate, so it is harder to decompose, it's harder to separate the sodium carbonate, sorry, it's harder to separate the reactive metal. Okay, so the most reactive metal here, we have 4 metals, sodium, zinc, calcium, copper. Most reactive is sodium, Okay, so sodium carbonate is the most heat stable. Explain why sodium carbonate is the most heat stable. Okay, so when we want to explain why it is the most heat stable, we have to talk about its resistivity to decompose, right? So firstly, is the most reactive metal compared to zinc, calcium, and copper. Okay, therefore, it has the highest resistance to decompose upon heating, and that's why it is the most heat stable. Okay, so this is the full answer. So sodium is the most reactive metal compared to zinc, calcium, and copper. So sodium carbonate has the greatest resistance to decompose by heating. Okay, therefore, it is the most heat stable. Just like the fridge and magnet analogy, right? The stronger the magnet is attracted to the fridge, the harder it is to remove the magnet. Okay, so the greater the resistance to decompose by heating for sodium carbonate. Okay, if no more questions, I'll move on to extraction of metal. Okay, so metals are found to combine with other elements in the earth crust called ores. Okay, so what exactly is ores? It's mainly your oxides, your carbonates, or sulfides. Okay, so metals on earth, right? Most of them will combine with, will exist naturally as ores. That means they'll be on metal oxides, they'll be on metal carbonates, and they'll be on metal sulfides. Okay, so for example, potassium, right, your most reactive metal, it will exist as potassium oxide, potassium carbonate naturally, right? It won't exist as potassium as an element by itself because it's very reactive. Okay, so it's very rare that that happens. And that is why we learn extraction of metal. Okay, we need to extract the metal from the ore. Extract potassium from potassium oxide, extract potassium from potassium carbonate. Okay, so the full definition of ore is a mineral or mixture of minerals from which economically viable amounts of metal can be extracted. Okay, so it's like your potassium oxide and then you want to extract the potassium. So there are two methods for extracting metals. One is electrolysis and one is reduction. Okay. Okay, specifically reduction with carbon. Okay, so for electrolysis, right, it will be your top four metals. Okay, potassium, sodium, calcium, and magnesium. Okay, before that, can you guys cancel out this aluminium here and then replace it with carbon and then add a hydrogen here. Okay, so they just change this. So this will be the normal reactivity series. Okay, so your top four metals will go through electrolysis. Okay, so we bring back the fridge and magnet analogy. Okay, let's look at the fridge and magnet. Now, right, the magnet is still a metal, but now the fridge is your ore. Okay. Okay, why can't I edit this? Okay, now the fridge is your ore, which means your oxides, your carbonates, your sulfates. Okay, so your top four metals, your top four most reactive metals, right? It will be strongly attracted to the ore, right? So it will form a compound that is strongly attracted to the ore. And therefore, it is very hard to extract the metal from the ore. It's very hard to separate the metal from the fridge, right, from the ore. So since it's very hard to do so, we cannot just use physical methods. We have to use electricity. Okay, so that's why for your top four metals, right? Top four most reactive metals, we use electrolysis. Okay, then everything below that, we can use a physical method. Sorry, not physical method, but we can use a lower cost method, which is reduction with carbon. Okay, also known as displacement with carbon. So your metals below carbon, you use reduction with carbon. Okay, So this brings us back to the displacement reaction, right? Your more reactive metal displaces a less reactive metal from its oxide or from a salt solution. So those metals below carbon, right? Zinc, iron, lead, copper. These metals, they can be extracted through reduction with carbon. Okay, so for example, right? Let's say your zinc or iron, right? Let's say you have iron oxide. Okay, let's say iron exists naturally as iron oxide and you want to remove it, right? You react it with carbon. So carbon, because it's more reactive than iron, it will displace it. Okay. Okay, it will displace iron. Therefore, this should be CO2. Okay. Yeah, it will displace iron. So it will form, that is how you extract iron. Okay, because copper is more reactive than iron, so it displaces iron from the oxide. But let's look at even below that, more below. We have like silver, we have gold. Silver and gold are your least reactive metals in the reactivity series. Okay, so they will exist as elements on its own. So because they are the least reactive, right, they won't form any compounds naturally. Right, they won't form any compounds naturally. They won't form any ores naturally. So they'll exist as your native elements. Okay, so silver will just be silver and gold will just be gold. So there's no extraction needed. Okay, usually we just mine them. There's no need to extract them because they exist as the element, as the metal on its own. So native elements are pure substance because they do not combine with other elements to form a compound. Okay. So that is it for extraction of metals. The main takeaway is there are two methods, right? We have electrolysis and we have reduction with carbon. So electrolysis is for your top four metals, and then reduction with carbon is for metals below carbon. Okay. And then metals below copper, right, like your silver, they don't need any extraction because they exist as an element on its own. Okay. And then the reason why the metals above need extraction because they exist as an ore, right? They exist as a compound naturally. That's why you have to extract the metal. So I hope this gives you a clearer understanding for extraction of metal. Right. If there's no questions, can you guys try question 4 and 5? Question 4. Rubidium is group 1 element. So which metal is most likely to be used in its extraction? Okay. So remember your group 1 elements, they are very reactive, right? As it goes down the group, they get more and more reactive. Rubidium is like almost at the end already. So rubidium is extremely reactive metal. Okay, so I'm gonna annotate that. Very reactive metal. So for your very reactive metal, which method do you most likely use for extraction? Most likely, it will be electrolysis. Okay. So let me explain why. The more reactive your metal, right, the harder it is to separate from its ore. Right? These very reactive metals, they naturally exist as an ore. That means your ore is your metal oxides, metal carbonates, metal sulfides. Okay. So it's most likely going to be an ore. Okay, so it's probably rubidium oxide, rubidium carbonate, because it's very reactive. So it's probably going to be a compound already. And we're going to use electrolysis, right? So that we can remove rubidium from the ore. Okay, so it's going to be electrolysis of its molten ore. We cannot do heating with carbon, right? Because carbon is not as reactive. So it cannot displace, it cannot reduce rubidium. And heating is all alone. Keyword alone. Rubidium, most likely it won't exist alone, right? Because it's very reactive. Most likely it will exist as an ore already. Okay. And the reason why aqueous rubidium chloride not accepted is because it is not an ore. Okay. Ore, right? What's the definition? It's a mineral or mixture of minerals from which economically viable amounts of metal can be extracted. Okay, it's only for your extraction of metal. So that's why your answer is B. Okay, sorry if my laptop has some sound because it's charging. Then I think got some like heat. Okay, question 5. Metals are found naturally as the metal or as metal compounds. Okay, either as the metal or as metal compounds. The metal compounds can be reduced to the metal using carbon as a reducing agent or by electrolysis. Which row is correct? So the metal that can be found as a metal will be your least reactive metal, right? Least reactive metal. Because only your least reactive metal, it will remain as the metal lah. It cannot react with other stuff. So we compare magnesium and silver. Which one is least reactive? Of course, it's silver, right? Silver is at the bottom of your reactivity series. So immediately I can eliminate A and D. Okay. Then obtained by reduction using carbon. These will be metals that are less reactive than carbon, right? Only metals less reactive than carbon, they can be obtained by reduction using carbon. So I see here there's a sodium, right? Definitely out. Because sodium is above carbon in the reactivity series. It is more reactive than carbon, so it cannot be extracted using reduction by carbon. Right, so your answer is C, because B is out. Okay. Yes, somebody raised a hand. Do you have a question? Please type up your question. Oh, okay. No worries. Okay, any questions? If not, we'll be moving on to the final part, which is prevention of rusting. Okay, this is a crash course, so I can't go through everything in depth, but I'll go through the most important parts. Yeah. So you realize I didn't go through the reaction with cold water, reaction with acids, all those, because I find that these other parts are more important. Okay. All right, if no questions, then let's move on to prevention of rusting. So before we talk about prevention of rusting, first we need to know what rusting is. Okay, rusting is when iron reacts with water and oxygen to form hydrated iron 3 oxide, which is your rust. Okay, so that is rusting. Rusting is when iron reacts with water and oxygen to form hydrated iron 3 oxide. And the hydrated iron 3 oxide is your rust. So if you have iron objects or steel objects at home, right, and then you see a rusting layer, that is iron 3 oxide. Okay. So I have a memory shortcut for the conditions of rusting. Okay, conditions of rusting. The memory shortcut is wow. Okay, so W is water. O is oxygen. And the other W is worse if salt/acidic condition. So there are only two conditions of rusting, which is the top two, water and oxygen. Okay, that means iron has to come into contact with water and oxygen in order for rusting to happen. And then what does the below one mean? Worse if salt or acidic condition. This means that rusting will be faster lah. That means iron 3 hydroxide iron 3 oxide will be formed faster if there is a salt condition or acidic condition. Okay. Right. So now that we know the conditions for rusting, let's go through the prevention of rusting. Okay, what can we do to prevent rusting? There are two methods in our syllabus. One is coating, the other one is sacrificial protection. Okay, we'll go through coating first. So to prevent iron and steel from rusting, a barrier between the metal and the conditions have to be placed. Okay, so you have to block the metal from getting into contact with water and oxygen. That's how you prevent iron and steel from rusting. Okay, think of it like you have a soldier, right? Yeah, I'm just gonna draw a stick man, and then you have your enemy. Okay, this is just very simple drawing. Okay, I label this guy. I label this guy as the soldier, and I label him as the enemy. Okay, so the enemy, he wants to attack the soldier. Okay, he wants to attack the soldier. What can the soldier do to protect himself? He can wear an armor, right? So let's say he wear an armor like this barrier over here. After wearing the armor, he is protected from the enemy's attack. Okay. So now we think of it. Now we think of the soldier as the metal. Okay, iron. Then the enemy is your conditions for rusting. Okay, so oxygen, water, and oxygen. And then this is the armor, right? Which is the coating. Okay, the coating of the barrier. So this is how the barrier works. It forms a barrier so that iron will not be exposed to water and oxygen. Okay, so that the soldier will not be exposed to the enemy's attack. Okay, so that is coating method lah. And there are few, it basically forms a protective layer lah. So that iron doesn't get exposed to water and oxygen, so that the soldier doesn't get exposed to the enemy. Okay, and there are a few methods of coating. We have painting, greasing, plastic coating, galvanizing, tin plating, and chrome plating. Okay, the most important one is galvanizing. This one is zinc coating. Okay, so galvanizing is the same as zinc coating. Okay, it means you coat the material with zinc. So all these methods, right, they act as barriers so that water and oxygen cannot come into contact with iron, okay, or steel. So that is coating. Next, we move on to sacrificial protection. Okay, so sacrificial protection is a method where the more reactive metal is preferentially oxidized. It's more readily oxidized compared to iron. Okay, so the more reactive metal corrodes in place of iron. So it sacrifices itself and corrodes in place of iron. Okay, so sacrificial protection can be done by connecting a more reactive metal to iron. So it's not necessary to coat the iron completely with the reactive metal. Okay, you just have to connect it partially. So let's use back the soldier example. I draw another soldier, and then I draw the enemy. Okay. Oh, my drawing is very bad. Okay. Now I label this guy as soldier 1. Okay, I'll show you in a second why. And then I label him as the enemy again. So now the second way is sacrificial protection, right? So what happens now is a more reactive soldier, he actually sacrifices himself. It is soldier 2, right? Soldier 2. Soldier 2 sacrifices himself to protect Soldier 1. Okay, because he's more reactive, he react to the attack faster. So he faster stand in front of Soldier 1 and then he sacrifice himself. So the enemy now attacks Soldier 2 instead of Soldier 1. Okay, then now I label all these. Soldier 1 is iron. Soldier 2 is the more reactive metal. And the enemy is, again, water and oxygen. Okay, so because Soldier 2 is the more reactive metal, it will oxidize more readily. Okay, so it will corrode in place of iron. It will get attacked by the enemy. It will get exposed to the water and oxygen and corrode in place of iron. So in the end, Soldier 1 doesn't get injured, right? Iron doesn't get corroded. Iron doesn't form rust. Okay, so that is sacrificial protection, where a more reactive metal sacrifices itself in place of iron. So some real life examples we have underwater pipes, where magnesium blocks are attached to the pipes at fixed position. Okay, so these pipes are made out of what? These pipes are made out of iron, okay, or steel. Then magnesium is actually more reactive than iron. Okay, if we look at the reactivity series, magnesium is more reactive than iron. So it will oxidize more readily, right? The more reactive metal will oxidize more readily and corrode in place of iron. Next, we have ship's hull connected to zinc block. Again, zinc is more reactive than iron, so it will corrode in place of iron. And then finally, steel legs connected to magnesium block. Again, magnesium is more reactive than iron in steel, so it will corrode in place of iron. Okay, so galvanizing is also a form of sacrificial protection. Remember, we talked about galvanizing as a form of coating, right? Even though it's a form of coating, it's also a form of sacrificial protection. Because even when the layer of zinc is damaged and exposes iron, iron will not rust. Okay, how come exposed but iron will not rust? Because zinc is more reactive. Okay, zinc is more reactive than iron. So it will oxidize more readily and corrode in place of iron. Okay, but for coating, right, if you use painting or greasing, once a small little layer is teared off, right, once a small little layer wears off, there will be rusting for the iron because the iron will be exposed to water and oxygen. Okay, only galvanizing will protect iron forever. Okay, because the zinc, even though the layer of zinc is damaged, zinc is more reactive than iron, so it will corrode in place of iron. Okay, so I hope this analogy helps you to understand prevention of rusting better. If there are no questions, can you guys do question 6 and 7? All right, it is 9:16. I'll go through the questions now. So question 6, iron can be protected from rusting by galvanizing and by sacrificial protection. Okay, which reaction takes place in either one or both of these methods of protection? So firstly, galvanizing, right, is basically zinc coating. So the reaction that will take place is zinc will be oxidized to form the zinc ion. Okay, so zinc will lose electrons. So reaction 1 is definitely one of the reactions. So immediately I can eliminate option C. Okay. Then next, sacrificial protection just means the more reactive metal will oxidize and corrode in place of iron. Right. So we have magnesium and copper. Copper is less reactive than iron, right? So it's definitely not a reaction that will happen. Because if copper is added, the only reaction that will happen is iron reacting, iron oxidizing. But magnesium can be a form of sacrificial protection because it's more reactive than iron. Okay, so let me just write some notes here. Okay, so that's why option 3 is out. So your answer is A. Okay, I'll be moving on to question 7. So this is your 4 marks question. One of the uses of copper is to electroplate it on steel to prevent rusting. Okay, compare the similarities and differences between electroplating and galvanizing steel in preventing rust from forming. Okay, so we have to link it back to preventing rust from forming. Okay, so I'm gonna paste out the answer first, then I will explain to you. Yeah, I paste the answer first, then I explain. So while you guys copy, you can just listen to the explanation. Okay, so for the similarity, right? Both electroplating and galvanizing steel is actually a form of coating, right? We learn coating. That is when there is a protective layer or there's a barrier that prevents oxygen and water from coming in contact with the steel, right? So it's like the enemy. You prevent the enemy from attacking the soldier. Okay, so that's your similarity. And you have to link it to preventing rust from forming, right? So it acts as the protective layer and prevents oxygen and water in the air from coming into contact with the steel. Okay, then the difference is basically sacrificial protection. If you compare electroplating with copper and galvanizing steel, right? Copper is less reactive than iron, but zinc is more reactive than iron. So zinc will oxidize more readily. So zinc will oxidize more readily and corrode in place of iron in steel. Okay, and because copper is less reactive than iron in steel, if the steel is exposed, right, that means some part of the copper is damaged, the iron will corrode. Okay, the iron will rust. Why? Because copper is less reactive, right? Iron is more reactive, so it will oxidize more readily and it will corrode in place of copper to form rust. Okay, so that's your similarity and difference. Which metal will displace lead from lead-2 nitrate solution? Wow, everybody got it correct. Good job. Okay, Varick is first place. Which redox reaction is least likely to occur? It is. I give you 45 seconds for this question. Which reaction is least likely to occur? Okay, so let me explain why the answer is green. So this is about displacement. Your more reactive metal will displace the less reactive metal from the oxide. Okay, so the first one we have magnesium and silver. Magnesium more reactive, so the reaction will happen. Then the next one you have zinc and iron. Zinc is more reactive than iron, so the displacement reaction will happen. Next we have calcium and magnesium. Calcium more reactive than magnesium, so the displacement reaction will happen. And finally you have copper and lead-2 oxide. Copper is less reactive than lead, but it shows that it displaces lead. That is very unlikely to occur. Okay, that's why your answer is green. Because copper is less reactive than lead, so it shouldn't be able to displace lead from lead to oxide. Okay. Our Yi Chen is now number 1. Which carbonate decomposes easily upon cooking? Okay, so the carbonate that decomposes easily will contain the metal that is the least reactive. Okay, so your least reactive metal here is copper. So copper 2 carbonate is the least heat stable one. Okay, now rhenium is number 1. Now the question is, which carbonate is the most heat stable? So the same 4 options. Okay, good job. Most of you got it correct. So sodium is the most reactive metal. That's why it's the most heat stable. Sodium carbonate is the most heat stable. Okay. Who is Pokemon? Which metal is extracted by the process of electrolysis? Okay, so for electrolysis will be your top 4 metals in the reactivity series. So please stop calling me potassium, sodium, calcium, and magnesium. Okay. Okay, now Varick and Pokemon has caught up. Which method is usually used to extract silver? So silver, right? Because it's the least reactive metal from the reactivity series, no extraction is needed because it exists as an element on its own. Okay, you don't have to extract it from any compound. Okay, good job. Which method of preventing rusting acts as both coating and sacrificial protection? Okay, good. Galvanizing is both coating and sacrificial protection because it's basically zinc coating. Okay. All right. Question 8. Okay, so your answer is green because magnesium, it will oxidize more readily, right? It's more reactive than iron in steel. So it will oxidize more readily and it will corrode in place of iron. So this is your oxidation reaction. Magnesium oxidized to form magnesium 2+. Okay, gene is number 2 now. When zinc is added to a solution of copper 2 sulfate, what observation is made? Okay, we went through this just now. So zinc will displace copper from copper 2 sulfate, right? Because zinc is more reactive than copper. So you will form zinc sulfate and copper. So copper is your pink solid. Then zinc sulfate is your colorless solution. So blue solution turns colorless. Okay, that's why your answer is blue. Okay, Lucas has caught up to number 4. Final question. Okay, correct. Because when metal react with dilute acid, it has to be able to displace hydrogen. Okay, then extracted using carbon, also it has to be less reactive than carbon. Okay, so zinc is your only option. So let's see the podium. Third place, we have Pokemon. Okay, good job. Second place, we have Jean. First place, we have Derek. Alright, good job, everybody. So now I'll share my screen back to the PDF. Okay, so can you guys scan this QR code and fill up the feedback form? So it really helps me like improve as a teacher. And I also will know what students like. Okay, so please scan this QR code. Just takes 2 minutes. Okay, then you have any questions, or if you cannot scan, right, you can also go to tinyurl.com/lchfeedback. Okay, then if you have any questions, just write down in the chat. Okay. I hope today's crash course was useful to you guys. Okay, then for those who already filled up the feedback form, thank you so much for coming today, and I hope you have improved. Okay, you guys can leave anytime you want.